5.2 properties of rational exponents and radicals. There are just going to be a lot of problems that I'm going to solve to help you understand how to simplify products or quotients of radicals. For starters, we want to review the exponent rules. So a negative exponent means you put 1 over it and it turns into a positive exponent. This negative exponent only refers to the second part of it, so it's going to be 3 over x to the 6th. Similarly, this is 4b to the 7th. Again, flipping that. Now, if this is a square, this is really this times itself, so it'd be a squared b to the 8th. You know, think about writing that 2 different times. Dividing, you subtract the exponents, so you pick where it's larger and subtract off the smaller. So that's going to be y squared. P really has a 1 here, so that's just going to be p to the 3rd power. Now, there are certain definitions of product and quotient property. It's basically just saying if it has the same exact radical, then you multiply the numbers on the inside, the radicands. And so it's the same idea with quotients, that if you have the same radicals, then you can divide those numbers as seen to the right. The other idea is to simplify. What is in simplest form of a certain radical? And there are 3 conditions. They have to have no perfect nth powers, so nothing can be pulled out of the radical. The radical can't contain any fractions, and the radical, no radicals can be in the denominator. So again, I think the easiest way to do this is by looking at examples. In this particular problem, we want to figure out, is there a perfect cubed number in 135? And so I know that 9 can go into it. If I add these numbers up and it's divisible by 9, then 9 can go into it, and that's how I figured that out. So that's where you have 9 and 15, and that's 3 and 5. So that tells me that this can be written as 3 to the 3rd power. There are 3 of them, 1, 2, 3. 9 is 2 more 3s, and times 5. So a 3 comes out, and a 5 remains inside it, and that would be the simplest form. Over here, this gets a little bit trickier. You're going to write it as the 5th root of 7/8. 8 is really 2 to the 3rd power. So if I multiply the top and the bottom by 4, notice that this is 32. 32 to the 1/5 power is 2. So I'm multiplying by 1. I'm not changing it, but now I can at least take this out of the bottom. It's rationalizing the denominator. And so now the 5th root of 32 is just 2. And on the top, it's just going to be the 5th root of 28. Same thing can be done here. I'll just do the first step. It's going to be, let's see, 12 over 27. 27 is 3 to the 3rd power. I need to the 4th power, so I would multiply by 3 over 3. I would just continue. And so this is going to be the 4th root of 36 all over 3. Notice you cannot do anything at this point because these are not the same radical. You can't combine them. Now, you also have something called conjugates. And a conjugate, the problem with this is that you have a radical in the bottom. So you want to get the radical out of the bottom. How do you do it? You're going to multiply the top and the bottom by the conjugate of the denominator, 5 minus square root of 3, which means that the top is 5 minus square root of 3. The bottom, 25. Notice what happens. 5 square roots of 3, negative 5 square roots of 3. Cancel out, and you're left with minus 3. So 5 minus square root of 3 over 22. Now, always check and see, can you simplify this? Does anything go into the 22 or number here? If you make this into two fractions, can it be simplified? And the answer is no on this one, so this would be your final answer. Another thing that you can do is combine like radicals. This is like terms. You can combine x's, combine y's. You're just going to think about that. There's 1 of these and 7 of these, which means the whole thing is going to be 8 of these. Same idea here, 12 times 8 to the 1/5. And then there's on one of the last slides, it's just a mixture of problems. So we're going to continue with solving some of these longer ones. Notice on this one, you're going to have 27 times 3. There are 3 3s, and one more 3 means 4 3s, and therefore that answer is just 3. So I don't want to multiply this. I want to just count the number of 3s and see if there are 4 of them, and then I can pull it out. On these, you can write it as one fraction. So it's going to be 25 over 2, which is 125, which means that this is going to be equal to 5. 5 times 5 times 5. On this one, you would multiply the bottom by 2 to the 3rd power. Multiply and the top by that. So this would be, because there are 2 2's, you want to do 3 more 2's, which is 1. And so now the bottom becomes 2 because there are 5 2's. And the top is going to be the 5th root of 3 times 8, which is 24. One other idea here is combining like terms. You can see that on this one, if I simplify this, this is 8 times 5. 8 comes out as a 2. 3rd root of 5. And now you can see that you have 1 and 2 of these, which means 3 of these. Now you can also have variables to work with. And when you have variables to work with, I would convert this to a rational exponent. So 64 to the 1/3, y to the 6th to the 1/3. In other words, you can take 1/3 of both of those, and now you can see that the first one is going to be 4. 4 times 4 times 4, 64, times y. 6 over 1 times 1 over 3 is multiplying fractions. You multiply the top, multiply the bottoms, and divide. Or 3 goes into 6 2 times. So you're left with 4y squared. Similarly, this one is going to be x to the 4th, y to the 8th. But you know what? You can take each of these to the 1/4 power. Notice I'm getting rid of those radicals and dealing with just fractions instead. So the top becomes 2x squared, and the bottom becomes y. Hold on a minute. Sorry, this is a 4. So the x becomes x to the 1st power, and on the bottom, y squared. So same properties with radicals and variables. It's just you have to deal with simplifying the fractions when you multiply them.